Alright, welcome back. Now we're going to try to get the floppy controller going.
I've hooked up, I've got it plugged in. I found
Actually new in the box, 5 1/4 MPI 51B single-sided drive. So should be the right kind of drive to use. So first thing I like to do when we get like an old card like this, we'll zoom in on it a little bit,
is just kind of like give it an overlook.
see what kind of chips are on there. It's quite an old card. It's from 1976, so we don't know the shape of it. We don't know the condition. We do have the manual for it. I'll post a link for it. But what I notice is we have some EPROMs here. And what I like to do before I put any power or do anything to these things is we want to dump these EPROMs. It's possible that there's no other dumps of it, or if there are dumps, which there are, I've found them, then we can compare the contents and see if it's the proper contents, and that gives us one step that we know that it is good. So what we'll do, and also I have a chip tester that tests some logic chips, so it'll test like the 08s and the 00s and the 04s, your standard gate logic. So what we'll do is we'll check all these that we can, that my tester will test. So just try to eliminate things right off the get-go, things that we can test. Then we'll fire it up, and we'll look at like the address lines and make sure that the signals are getting through the buffers and the data line, just to make sure that the signals are getting through to the board. So we'll check as much as we can that way, and then we'll fire up the software, see what we're going to do. So what I'll do is I'm going to start popping out some of these chips. We'll go with these EPROMs here. So they do have a little code on them. Okay, LE8. So we'll put this into the chip reader. And we'll fire up the handy dandy chip reader. That would be a Prom and National Semiconductor. And these are 287, I believe. S287. So there we have it. And what we'll do is I've loaded what's supposed to be on the chips into my program. So 8 binary file. So now what we'll do is we'll read the chip into red, and now we'll compare it to what's in the buffer. Verify. And it says it verifies it's okay. So that we know that that chip has got the proper contents in it. So we'll throw it back in. So that's promising. And we'll go with the next one. chip reader. I'll do a video on the Universal Programmer chip reader. The one I have is actually quite old, and there's quite a story to it, and that's a whole other video. It's actually quite a humorous story how I ended up with this thing. It's quite old, and it's a DOS-based program, but it does a lot of old chips. Does a lot of testing of things. It's it's very robust. It uses all kinds of voltages off the ISA port, off the ISA bus, and I don't know. Haven't really found anything better for working on the old stuff that's reliable, and it does so many different variations of chips. Well, let's load up this one. Read, verify, and that's verified good. So that's 2. So that's the main software. And the third EEPROM, from what I read in the manual, is actually it's for doing the address decoding. So it really, actually, this thing only has 3 values in it. And so when the address gets selected, then it outputs. So it's basically a chip select. They've used it as a chip select. It's kind of a neat way to do it instead of using logic gates. So let's see if we got anything happening there. We'll load up that one. These chips are quite hard to come by, so if one was dead, it would be a little bit of a process to try to get a replacement. Actually, I probably do have a replacement because another older my computer uses these type of chips. And then we will read. Verify. Actually, let's look at this one. There it is. You can see that it's actually 4 digits. So these are only 4-bit chips. So you got to ignore the first, where all the zeros are. It's just, so the chip's filled with F's, except for right there, A977. So those are that's the chip select. So when the addresses are selected, this address, so it'll be 10, 11, 12, 10, 11, 12, 13, 14, so 15, 16, 17, and 18. And each one of those gets selected, it'll put that A977 out on the data bus, or on the output, the data out chips, and they've used it to select different things on the board. So it's not really an EEPROM that runs, it's more used as a chip select, so it's just kind of neat. So that's good. All our EEPROMs are good. So what we're going to do now, we'll get out of here. Go over to the tester. I'll show you how this works actually. So I put a 7.4 LS11 in the tester. So we go type 7.4 series, check the number, we'll get an 11, then we can do a function test, test OK, and then we can do a loop test, and that just kind of runs it a little bit. Excellent. So that chip is good. It won't test all the chips, and we could test each one individually by making a little test circuit. But it doesn't look like any capacitors are blown. There's no like burning on the thing, so it's we'll try this 08. Sockets aren't very great. They're pretty old, so we might have some socket problems. But we'll try to eliminate as much as we can right off the get-go. So we'll change the number to an 08. And then we'll do function test. Good. Loop test. Excellent. So we'll just keep rotating through all these, and we'll come back once I'm done. Alright, well, we came across our first bad chip, 74LS30, so I'll just show you what happened here. So we'll do a function test. Error. Loop test. Error. So, that is not good. We found our first bad chip. And I believe I have another one of those. I'm going to replace it, and I'm going to keep going. And if we find any more, we'll come back. Alright, now that we have the tested as many chips that we could test with the tester, the EPROMs have been checked. Let's we go to the manual. It has a checkout procedure, so we can start checking some waveforms and compare them to what it says in the manual, and hopefully we can get a little farther, and we'll go from there. So the first thing in the manual, we are going to look at chip 6A. It's nice. This board is labeled rows 1 through 9, and then the chips are, and then columns 1 through 9, and rows A through G. So it makes it nice and easy for pinpointing things on the schematic, and also in this checkout guide. So pin 6A, chip 6A, pin 5. 6, pin 5. Okay, let's hook the ground up to the oscilloscope probe. Okay. We are supposed to have a 500 nanosecond square wave. The output of the oscillator, half the crystal frequency. So it's a 4 megahertz crystal, so we should see 2 megahertz is exactly what we have, and our period is 500 nanoseconds. So that's perfect. Next, chip 2A, pin 11. 2A, pin 11. 11. We are supposed to have 7.5 microseconds, almost a square wave. This is the signal in the data separation circuit. Let's see if we can tighten that up a little bit. Pin 11. 7.5 microseconds is the period, and it's pretty much a square wave, so that's perfect. This is a good sign. Chip 2B, pin 11. 2B, pin 11. These are counter chips. Shrink that up a bit. We are supposed to have 120 microsecond period, square wave. Count the bits during the read period. That's 120 microseconds, right on the money. So 1D, pin 11. 8 microseconds. And that's at 8 microseconds. Period is 8 microseconds. Pin, that was 1D, now pin 2D, pin 11. These are obviously the tops of the clock. Okay, what are we supposed to have here? 2D, pin 11, 128 microseconds, perfect. Unity square, continuously running counter with period equals 16-bit cell times. 1E, pin 11. And we have two milliseconds. And that's what we have, 2 milliseconds. Square continuously running counter with period equals 256-bit cell time. So this would be for the bits that are getting written to the disk. Okay. 2E, pin 11. So these are all the counters. Oh, 2E. So we're still ready. 2E. Okay. Crank this puppy up. 2E, pin 11, 32 milliseconds. 32 milliseconds is what we have. Square counter with period equals 1 sector time if sector pulse being received, period, is equal to 4,096 bit cell times otherwise simulated sector time. So that's working there. 1G, pin 11. Just round down to the bottom here. 1G, pin 11. Third, 320 milliseconds. And that's what we have. 327. Close enough. About 20% of the time high. Yep. So that's 1 disk revolution. Perfect. 1F, pin 11. 5 seconds. It's a big one. Shrink this up. Get it to 5 seconds. Okay, let's go 1 second there. This might take a little bit of a while to acquire. Come on. There it is. 5.2367 seconds. Very good. Alright, so that's the first step of the checkout. And we'll move on to the next phase. Okay, the next step. Examine the first 2 cells of the onboard Prom memory and verify it against the following table. The addresses given are good for only the standard version. However, the values given should be the first 2 bytes even if in the non-standard version. So what it's asking is to see if we can address the board and look at the Prom memory. So what we'll do is we will dump E900 to say E910. So our first 2 digits that we should see should be 31 and 14. There it is, 3114. So it's addressing the board properly. And then it's finding the proper values in the ROM. So far so good. Seems to be that a lot of things are working out. So let's move on to the next phase. Alright, this phase, let's see what it says. This step is for checkout of the data read and decoding logic. The ribbon cable should not be plugged in. Tack solder a jumper to 1D pin 12. So we're not going to do that. We're going to just use a jumper. 1D pin 12. 1D pin 12. And then we'll add this to the bottom of resistor R6. So this is obviously going to be putting a clock signal into the circuit to simulate data coming in from the floppy. Let's just make sure we have something there. Okay, that's a little bit big. Let's get it up on the scope. Shaky hands. Pin 12. Can I get my hands on there properly? There we go. So we have a signal coming in. What do we have this set up here? Not working properly. No signal. Why is everything coming from behind so much here? Restart this thing. Alright, there we go. Okay. Pin 3A, pin 6. This is nice read data is the signal called. We should have the jumper connected. A 0.5 microsecond pulse every 4 microseconds. So our period is 4 microseconds, yep. And the width of the pulse is 500 nanoseconds, which is 0.5 microseconds. So that is correct. And so without a signal, it should be always low. So we're good. Okay, the next one, so that's nice read data. Now separate data. 6B, pin 6. So 6B, pin 6. Unstable here with my jumper. There we go. What do we need? 0.5 microsecond pulse every 8 microseconds. So yeah, 8 microseconds with a 500 nanosecond, which is 0.5. Perfect. And so unconnected, it should be always high. Yes. The signal's a little bit noisy. Okay. Read bit shift. Pin 2A 15. 2A pin 15. Now we should have a 0.5 microsecond pulse every 8 microseconds. So we're at 8, and it's read bit shift pin 2A, pin 15. 0.5, which is what it is, every 8 microseconds, which is what we got. So that's connected. So unconnected, it's supposed to be 0.5 microsecond pulse every 7.5, and that's exactly what we have. Excellent. This is looking good. Saved read data 9G. Pin 9. So 9G, pin 9, which is way down in here. And then we're supposed to have connected. My jumper's not 100% good there. There we go. 8 microsecond period square wave. It's pretty much a square wave, and the width is 4. So yeah, pretty much close, right on the money. All right, unconnected should always be low. Good. So far things are going good. All right. Read shift register, pin 5E, chip 5E pins, so 5E, that's way down in here. So connected we have, let's make sure our signal's still going, yeah. Pins 3, 4, 5, and 6. Okay, got the signal still. 5E, pin 3. So when it's connected, always high. So pin 3, 4 should be high, 5 should be high, 6 should be high, 10, 11, 12, and 13 all should be high. 10, 11, 12, 13. Okay, and unconnected, they should all be low. Low, 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 low. 10, low, 11, 12, 13, low. Okay, well, that's the next phase checked out, and everything seems to be working. It's all like right on the money for the data sheet. So next, we'll move on. Alright, this step checks out the timing signals for reading and writing. The drive should be powered on and the ribbon cable should be plugged in. So we're getting close. We're hooking up the ribbon cable. Power up the drive. Alright. So we got to enter a little program here. So I'm going to enter that up and then we'll be right back. Okay, that program's entered now. What does it say to do? Scope, edge triggered on the signal sector flag, 6A pin 8. So let's hook up 6A pin 8. Circle the ground. And Set up the trigger. Trigger edge, positive going edge, channel C1. Alright. Okay, the trigger's set up. So let's see what happens if we run it. Nothing, because it's not running. So let's run the program. So that's EX at 2000. Oh, there we go. It triggered. So now, let's go to the first one. So high for sector flag, 6A pin 8. High for 30 to 40 microseconds. And we're at 50 scale, and so that's about 30 to 40. Well, that's a good thing. So the next signal is called window, 9F pin 6. 9F pin 6. Start it. What should we have here? Window. High for 96 microseconds. And we're at 50 microseconds. Am I on the right pin? Pin F. 1, 2, 3, 4, 5, 6. Shot. Okay, something's happening. I think we have to change the scale here a little bit to bring it in to form. Nothing.
Okay, let's just make sure everything's working here.
Alright, the first test is going to be sector flag. Let's start it. High for 30 to 40 microseconds. We're at 100 microsecond scale, so that's about right. Window 9F pin 6. And that should be high for about 96 microseconds and low. So that looks about perfect. Trans is the next signal. 9F pin 9. Sneaking down in the bottom here. Get rid of my mouse. That's supposed to be 8 microsecond positive pulse after 96. That's not good. That does not look right. But I'm not on the right chip. Pin 9. There it is. 8 microsecond positive pulse after 96. So that's at about 96. And then a positive pulse. And that probably, let's go to the look at the measurement. And the width is 8 microseconds. So that's perfect. And our next signal is Hunt 9E pin 6. 9E pin 6. Okay, let's shrink that up a little bit. Fire it up again. So Hunt signal, what is it supposed to do? Low for 480 microseconds, then high on our trigger. And that's at 500 microseconds, so yeah, that's about 480. Spread it out a little bit here. That's 200 pulse, so 2, 4, that would be 5, that's about 80. So that is correct. And right request, 9G pin 6. Way at the bottom, 9G pin 6. And that's supposed to give us low for 60 to 75, then high. So, let's go a little bit. So if that's 20, right request, 60 to 75. So that's really only 20, only around 30. It's about half of what it's supposed to be. So let's make a note of that. That might be a situation, but could be a typo too. So far all the other signals are working quite well. The next one, 9E pin 10. This is right signal. 9E pin 10. 10. This is supposed to do low for 104, then high. So shrink that up a bit. 50. So that's 100 is the scale. So low for 104, which is about exactly right. Take a look up here on the width. Negative width is 104, so it's perfect. And write data is our next one. Chip 8B pin 6. 8B pin 6. And that's supposed to give us high. 8B pin 6, am I on the right one? 8B pin 6. Wrong pin. Oh boy, here we go. I can't see where my cursor is because I got the cameras right in the way of my screen here. So, let's shrink that one more scale. What it's supposed to do. High for 104 microseconds, then 8 negative pulses at 8 microsecond intervals. So that's about, what do we got? What's our scale? 50. So 50, yeah. 100, and then 8. Zoom in on these ones a little bit. The width of those is 8 microsecond intervals, yep. And a bunch of pulses. Just kind of randomly at 4 and 8, that's about half the distance. So 100, then some write data, and it's just all mixed up. So that is working 100% so far, other than the one that seemed a little bit off. It was about half the distance, so it's possible as a typo, but maybe not. We'll see. If the thing doesn't work when we go give it a test, then that's one of the places we can look, because everything else was bang on except for that one write request. Low for 65 to 75 microseconds. We're only at about 35, so about half of what it's supposed to be. Okay, let's see what the next step is. Alright, well I think we're just about done through the testing. Let's see what our next step would be. Plug it all in. Turn on the computer, the disk drives. We're going to enter a small program. Set this. So we'll enter a small program at 2000, so that's EN for enter. 2000 is the address location. I'll go up, we can maybe take a look at this. Zoom in a little bit. So we'll
we'll enter the little program.
3A 80 EB, so that's load A at address EB80. And jump to itself. C30320. So what that should do
is we'll swing back down here. Where's our camera? There we go. There's the disk drive.
So if we run this EX2000, it is telling us the program should cause the motors on all the drives to turn on. The automatic motor turn off should cause the motors to stop in about 5 seconds. There we go. Okay, that started it and it turned it off after about 5 seconds, so that's working. Examine address EB 20. This should cause the MDS controller to place the B status byte on the data in bus. The sector position field, low order 4 bits, should constantly change with the value between 0 and 9. Okay, so we'd have to hook up the logic analyzer to see that, so we're going to skip that step. If we end up that it's not working or something, or we're having problems, maybe we'll come back and take a look and see if that could be a problem. But so far everything else seems to be working. So it says, with no diskette inserted in the drive, starting the bootstrap program at address E900 should cause the following actions to occur. The motors for all the drives will turn on. After 1 second, the head will load. That will be a loud click. The disk heads will now step out to track 0 to 35 in muted clicks. After this, the computer will endlessly loop within the Prom program. Okay, this is a newer Prom program, so from what I understand, it will just do this once and then time out, so it just doesn't endlessly loop. So let's give that a shot. Reset the computer. So we want to execute at E900.
So what should happen is the disk
there's no disk in there, so it should act like it's going to try to boot. With the light. And it turned off because I didn't find any boot sector.
Alright, so what that's, it's really checking out like it's going to be good.
So I think that's a pretty good video for today. We're going to end this now. And I'm going to get more organized. Our next video we're going to show how, well, the box of hard sector discs I had are 16 sector discs. This controller needs 10 sector discs, and they're really hard to find. So what we're gonna have to do is we're gonna have to try to make one or find one before we can even get ahead here. So we're gonna move out on the next phase. We're going to try to get a disk. We're going to try to write a boot disk. And we're going to try to boot the computer. So let's see where we're at. And we'll go from there. But the controller seems to check out with all the signals. So it's really positive. So if we can get a disk, then maybe we can make it boot. So until next time, thank you for watching, and we'll talk to you soon.